All right, let's take a look at how the conservation of energy is actually applied. We're going to get some help from some Yetis here today. We examine this idea that in a closed system, as long as we consider all of the objects, the momentum always has to stay the same before and after. So here we go. We've got the mass of our Yeti and the mass of the car. And no collision has happened yet, but here is two separate objects, the Yeti and the car, which is behind the Yeti. And the question is, what's the momentum in the system? So system, that means everything. So all of this stuff, what's the momentum of it? And our way of notating this is using the sigma, which means the sum of all of the momentum. And it's the sum of all the vector momentum. So it does matter that they're both going to the left instead of to the right. So any vector that's to the right is positive and the left is negative. So I just need to add the momenta of both of these together. So it's pretty straightforward. Momentum is just mass times velocity. So I have the Yeti's mass, 300 kilograms, and his velocity of 2 meters per second. But I'm going to be careful about that because the Yeti's going to the left. That's going to be negative 2 meters per second. And then I'm going to add to that the momentum of the car, which is 800 kilograms, and has a velocity of negative 5 meters per second. And you could do this for any number of objects. I could give you 10 things and ask the momentum of the system. You just need to add up the momentum for all 10 objects. So in this case, when they're both added together, I get negative. So a net motion to the left as everything moves to the left, 4,600. And the unit for momentum is the kilogram meter per second. So it's very easy to find the momentum of the system. We just find each part and we add them together. We just got to keep track of whether things are positive and negative. Now, let's try another one here. This time we have something a little bit more complicated. I have an object going to the right and one to the left. So I'll just take note that this is going to be a negative velocity and a positive. Here I've got a Yeti and a car together moving to the right and then a Yeti moving to the left. And so again, for the whole system, it's all three objects, both Yetis, the car. What is the total momentum of the system? So same idea. I'm going to add up all the vector momenta. And I could do this. I could either treat this Yeti as his own thing moving at 2 meters per second and then the car moving at 2 meters per second, or I could just treat them like one big object. It comes out the same either way. I'm just going to treat them like one big object. So the Yeti car is 300 kilograms plus 800 kilograms, the mass of both of them. And then together, that mass is moving at 2 meters per second. So that's the amount of momentum that's moving to the right. And then I have a second Yeti who has a momentum to the left. So, I mean, I'm not really sure how this is going to turn out. It depends on which of these two is bigger, whether the system has more momentum to the right or to the left. And it's really useful to know that because if I know which way the momentum points, I know what's going to happen after they interact with each other. So if they run into each other and the total momentum happens to be positive, then they're going to keep going to the right with a positive momentum. On the other hand, if the total is negative, then they're going to get swept off to the left. Or it could even be that these two add up to 0 and that they're going to hit and stop. Very useful to know. So in this case, when I add up all the numbers, I get a small momentum because there's a lot of canceling happening between the two numbers of 400 kilogram meters per second. And so that gives me an expectation of what's going to happen after these things interact with each other, that they're going to hit and there's still going to be some motion to the right, but it's just not going to be a lot of motion, not very much compared to the amount of momentum they had before. Okay, flip over to the next page. And before we try this problem, here we're looking at a before and after situation, which is really where momentum conservation is the most useful, looking at the system before and after. And this was in the previous video or our previous lecture. So if you haven't put it yet on your equation card, now is your time to do this. Sigma P sys 1, so I'm going to add up all the momentum in the system at the beginning, in this case it's this picture here, is always equal to sigma P sys 2, all the momentum of everything and the end. That's why it matters to us what the momentum of a system is, because as long as it's a closed system, as long as nothing's coming from outside, it's just the inside things interacting, and I take into account all of them, the momentum has to stay the same. So let's see if we can use that to make a prediction here in the case of the Yetis. How how fast was the Yeti moving before he jumped on the car? So we have a car that's going to the left. We have a Yeti that's going to jump on, and we don't know how fast he's going. But then after the Yeti jumps on the back, they keep going in the same direction at 14 meters per second. So here's my system. It's all the interacting objects. And as long as I take them into account before and after, this is really my preferred way of drawing the picture too. I draw the before and the after picture. I like putting a slash in the middle, because then what I can do is I can just drop my equals sign in right under the slash. So whatever momentum's here has to be there. So let's figure this out. So sigma p sys 1, I'm going to add up all the momentum in the system at the beginning. And that has to be equal to sigma p sys 2, all the momentum in the system at the end. So let's see, I've got two objects here. I've got my car, which is 800 kilograms, and it's going 8 meters per second in the negative direction. So I have some negative momentum from the car. And then I have the Yeti, 300 kilograms. And I don't know how fast the Yeti's going, so we'll just call that velocity V. So we'll call that V, what we're looking for here. And then afterward, the two, it looks like they've stuck together. The Yeti's on top of the car. Believe it or not, I found an image of a Yeti on top of a car. Kind of proud of myself there. So they're just one object that's equal to the mass of both of them. So 800 and 300 add up to 1,100 kilograms. And together they're moving in the same direction the car was originally going, 14 meters per second, but it's going to be negative because they're going to the left. So some extra speed has been gained due to the Yeti jumping on the back, but the momentum of the system has to stay the same. So you can see at this point now I can solve for what this unknown V is. And we find V. It seems like Yetis are pretty fast. 30 meters per second is about 60 miles an hour, but this Yeti jumped onto the car at about 60 miles per hour and made the car go faster when he jumped on the back, but it slowed the Yeti down. It slowed him from 30 to 14 when he jumped on. Very useful idea, the conservation of momentum. All right, let's check out another one. This is one of my favorites here. You can check out the movie trailer. I'll provide the link for this. I remember this movie came out when I was in high school, maybe a freshman in high school, 1996, a long time ago. Arnold Schwarzenegger seemed to be in every action movie in those days. And I remember in the movie, it was a pretty crazy movie, a little bit ridiculous, as you'll see from the trailer, but they used this device called a railgun, which there really are things called railguns. I'll give you a link for those as well if you're interested. But a railgun purportedly was shooting objects at close to the speed of light. And so you kind of see those in the trailer. And I was thinking about the physics of that. Like, what would happen if you held a gun in your hand that was able to shoot a bullet that fast? What would be the effect of that? So we'll do a quick calculation here. This number is actually very much exact because as a professional bodybuilder, Arnold Schwarzenegger's mass was known precisely. In 1996, he had a mass of 114 kilograms. And I don't know how big the bullets were, but we'll assume very small. We'll say about the size of a paper clip, half a gram. And reaching the speed of light is problematic. Weird stuff starts to happen with the physics there. So we'll assume half the speed of light for the shot. Okay. So the question is, what will Arnie, or Arnold Schwarzenegger's final speed be after firing the railgun? And then how much kinetic energy will the projectile have? So first of all, let's understand why Arnie's going to have some speed after firing it. And I'll model for you here the basic idea of how we set up these problems. He's got big biceps here. We'll give him big biceps and have him maybe in a kneeling position here, shooting his gun. As he fires the railgun. This is a little buzz cut there. That looks exactly like Arnold Schwarzenegger. This is him before he pulls the trigger. That's my before picture. And then in the after picture, there's going to be a little bullet that's flying forward really fast. And as a result, if you've ever fired any sort of firearm before, you've noticed that there's a recoil or a kickback that happens. And we talked about this a little bit when we did Newton's laws, particularly Newton's third law, where every action is an equal and opposite reaction. So here's our muscular Arnold Schwarzenegger. As he, oh goodness. as he goes flying backward. Okay. So there's going to be quite a bit of a recoil from firing a projectile this fast. And the reason that guns recoil is because of the conservation of momentum. As long as I consider all the objects in the system, the momentum has to stay the same. And if I look at the system, which consists of Arnold, the gun, and the bullet that's inside, nothing's moving at the beginning. So this is a zero momentum system. So that means after he pulls the trigger, it must also be a zero momentum system. If something goes forward, something else has to go backward. And in our case, it's Arnold Schwarzenegger holding the gun, and we need to figure out how fast his speed is. So let's just put the numbers into the picture. Let's see, we know his mass, 114 kilograms. We know the mass of the projectile, 1/2 gram. And we know that it's going 1.5 times 10 to the 8th meters per second after he pulls the trigger. That's all my given information. So again, if I draw my good before and after picture, what I can do is I can just slap that equal sign right here in the middle. And whatever momentum is in this picture, sigma p sys 1, has to be in this picture afterward, sigma p sys 2. So this one's pretty easy because nothing's moving at the beginning. There's no momentum in the before picture. And the after picture, we've got Arnold Schwarzenegger's mass, 114 kilograms, times some unknown velocity. That's what we're looking for, trying to figure out how fast he's going, plus the mass of the bullet. And I have to be careful with this. I have to change it into kilograms by dividing by 1,000. So it's going to be 0.0005 kilograms. So almost no mass at all, but moving at a ridiculously high speed, 1.5 times 10 to the 8th meters per second. So when we go to solve for what's going to happen to Arnold Schwarzenegger after firing a railgun, we find that his final velocity is negative 658 meters per second. 658 meters per second. So that's well over 1,000 miles per hour that he's going to go flying backward. Needless to say, if you were holding a gun like that and you fired it, you would basically kill yourself. Or at the very least, blow the gun out of your hands and have it go flying backward at lethal speeds to anyone that was standing behind you. So that's a bit problematic with a railgun. And if you look at the video links that I share, you'll see that real railguns are always really big, and they're connected to large objects, big concrete bases or battleships, so that if we made this mass a whole lot bigger, then the velocity will be smaller for the recoil. Okay. Railguns are real things, and so this was part A of the problem. The military is very much interested in them because if you could fire even a paperclip at half the speed of light, you could create a pretty devastating effect. And that's the final question: how much kinetic energy does the projectile have? So if you recall from our energy unit, kinetic energy is 1/2 mv squared. So 1/2, the mass again, 0.0005 kilograms. So you're thinking probably not much energy because not much mass, but look at the speed, 1.5, write this right, 1.5 times 10 to the 8 meters per second. And then that gets squared. So we go to find this speed, it comes out to be 5.6 trillion joules. Now that sounds like a lot of energy, and it is. It's about the energy as what the military would call a MOAB bomb, which is the largest non-nuclear weapon that the military uses to destroy like underground concrete bunkers. And again, there are no explosives involved here. It's just a piece of metal the size of a paperclip, but it has so much kinetic energy, it's essentially going to vaporize anything it touches. So again, check out the video link of the actual railgun firing, and you'll see an example of what this kind of energy looks like as it blasts through steel armor. Okay, so there's a pretty simple example of how conservation of energy might be used, or conservation of momentum, I should say. Let's do one last one together. Number 5, we have some gliders on a frictionless air track. When I get a chance, I'll show you this air track. We have 2 different masses, glider A's mass and a certain speed, and it collides head-on with glider B, which has another speed, or also the same speed, 2 meters per second. Then I know the final speed. Oh, it's easy to get lost in a problem like this. I really need to draw a picture of these gliders. It looks like glider A is a little bit larger, so I'll draw it a little bit bigger. So here's glider A. It's 1/2 kilogram. and it's going 2 meters per second. Doesn't say which direction, so we'll just pick to the right. Then it collides head on with glider B. So glider B is a little smaller, only 0.3 kilograms, also going 2 meters per second. But here's where I got to be careful. This will happen a lot of times in problem solving. It doesn't say that one is positive and one is negative, but drawing a good picture will help me catch that. B is going to have a negative momentum. A is going to have a positive momentum. This is before they run into each other. There's no friction, so no outside forces. It's really just these two objects, and whatever momentum is in the system has to stay in the system. Like what happens in Vegas stays in Vegas. And then what do we know? Glider B has a final speed of 2 meters per second. So after the collision, glider B's final speed is going to be 2 meters. Well, that's weird. Glider B had a speed of 2 meters per second before the collision. So the only reasonable way that it could still have the same speed after running into something is it still can't be going to the left, or it would pass through glider A. It must have bounced back the other way. So it must now be going at positive 2 meters per second. And then the question is, how fast is glider A going? Is it still going to the right? Has it bounced back to the left? Wolfeye, does it stop? Any of those are possibilities. We don't know. But as long as we consider both objects, then that momentum has to stay the same before and after. So we'll do sigma p cis 1 equals sigma p cis 2. Add them all up and we'll solve for the final velocity of A. Okay. So let's see. For the initial momentum, I've got the ½ kilogram glider going positive 2 meters per second, plus the 0.3 kilogram glider going negative 2 meters per second. So that's the starting momentum. And then afterward, we have our ½ kilogram glider with an unknown final speed. And then the 0.3 kilogram glider going positive 2 meters per second. And again, setting up and solving these problems is really pretty easy. The place where you've just got to be oh so careful is when things are positive or negative, because if you don't get the signs right, it's going to mess you up. And drawing a good picture is so important to doing that. So don't skip that step. Draw the picture, draw the before and the after, and the problem sets itself up for you. Okay. So if we plug this into my calculator, figure out what these are, subtract this term, divide by 0.5, we can get the final velocity of cart A. And it comes out to be negative 0.4 meters per second. So this is really cool. I now know how fast A is going, and the fact that it's negative means that I also can predict that it's going to bounce backward off of B instead of continuing to move forward. I hope that's helpful to you. You've seen some examples now of how this works. Now you got some to try on your own. Knock yourself out.